Okay, sorry, we're behind schedule. Is anyone in a big rush tonight? No, that's good. So I haven't done a full run through of this talk. It might be an hour talking, it might be slightly more. Then I've got a demo at the end, and then obviously there's time for questions depending on where you're at. If you want to get the hell out of here or ask me awkward questions at the end, it's all good with me. I'm going to share the presentation by these guys, so that will be available on Twitter or something, I don't know. And the code that I've put together is already on GitHub, and those guys will have the link for that as well. So let's get into it. Hi. To introduce myself again, I'm Duncan, as Val said. I've been programming for about 20 years at this point. I didn't do computer science. Did anyone in the room study computer science? Oh no, almost everyone. Okay, so it might actually not reveal all that much to you guys. Maybe it will, I don't know. There's another question I should ask. Is anyone super into databases? Like, is that someone's thing here? Okay, at least we've got that in common. Right? That's good. So maybe you've forgotten all your database-related computer science knowledge. We can only hope. Anyway, apologies if any of you do find this like really boring content. Anyway, let's get into it. This talk has got a very high chance of exposing my ignorance in a lot of areas. But do you know who this person is? Brené Brown, right? Yeah. So she's on the internet making tons of money, telling everyone that it's really good to be vulnerable. I'm just like trying it out tonight. I'm totally vulnerable at this point. Might sound like an idiot, but she's raking it in, so can't be bollocks, right? Anyway, here's what I reckon. Like this represents me during pretty much my entire career. To explain that a little bit, it was a stance that I took very early on. At the time, I was busy demystifying C# and programming in general. And I found that C# was a really good tool for doing that because the abstractions, although they're there, they're quite easily unwrapped. So, for example, it seems like events, maybe they are just the observer pattern, right? For those of you that don't know this book, it was some kind of Bible, I don't know, maybe it still is. It was written by 4 guys, hence the name, the Gang of 4, and it was the first book to really lay out the standard set of design patterns, and I'm pretty sure that every single programming interview that took place in the 90s included a question on a design pattern, right? And it's normally swiftly followed by drawing a linked list on a whiteboard. Val's desperate to get to a drink, we should just grab on. Okay. So what else was I wondering about at the time? Stuff like how does for each work? Well, okay, again, that's just the iterator pattern. This book right here, this, I think, in my opinion, was the book that everyone was reading and then saying they read the other one. This was like the one that made it quite easy and accessible. Is that book familiar to anyone or not? Yeah, some of you have noticed them. And we're all still trying to figure out if that actually is Whitfield on the front cover or not. Maybe she was short of money. I guess all those Saturday nights start adding up at some point. So what about something outside of the Gang of 4? Like, for example, how does a garbage collector work? This one is definitely not standard. But then again, the people that were building the platform were there to offer the help. And there was a ton of content like this available, and I was lapping it up. And I feel like because it was a new platform, there was a whole bunch of people looking for this type of content, and our collective enthusiasm made it economically worthwhile, the people that were building it, to put this content out. And aside from that, Microsoft had a commercial interest in the uptake of the platform. So they were sponsoring a bunch of official documentation, and they were sponsoring stuff like the MVP program and user groups like this. And plus also it was the heyday of the blog. So that was another route to information that was available to me. All of which made, you know, the deconstructing the art of programming like really super accessible to me, which was really helpful because back then I knew nothing. I hadn't done computer science, like I said, so I was trying to bootstrap myself. And then it came to databases, right? How do databases work? And in contrast, at least as far as I could tell, this was the answer. Don't worry about it, they just do. So back to the story of me as a young programmer, there was this big black box in my world that just worked. As long as, and this is the thing, right, the caveat, as long as you know the spells. And what were the spells? Well, as I remember them, they were something like this. Normalized like it's 1999. It actually was, which was helpful. Enforce constraints, use primary keys, index stuff to fix things. If you don't know what you're doing, just start doing that. If you do know what you're doing, or you're pretending to know what you're doing, pull out the query analyzer and stroke your beard for a while. Then start building indexes. When things start going wrong, indexes slow down. Oh dear, that's bad. Maybe you should reconsider your life and maybe not start adding indexes. Number 6, indexes can chew up disk space, and this can be bad also. Maybe that's another reason to not use our only tool in the box. Indexes can go bad with time. I actually don't know what to do about that one. It sounds like someone else's problem. Number 8, they're getting increasingly more relevant. Number 8, all projects need a database wizard. You should find the database wizard. And then most critically of all, make friends with the project database wizard and buy him beer, because sooner or later he's going to save your ass. So it seemed to me, and it kind of still does, that apart from mastering a set-orientated programming language, which kind of blew my mind, because like I was saying earlier, I was getting fairly deeply into the world of procedural and object-orientated programming. I always say that word wrong, orientated programming. And then to chuck set-oriented in there in the mix kind of just blew my mind and gave me a major procedural existential crisis. And the other thing it seemed to me was like indexes are both the solution and the actual problem to all things database. So what do you think I did? I chose number 9. That's me on the left. I love that guy. He always smoked afterwards. Best wizard ever. So that's the background. So you're probably sitting there thinking, well, then why are you sat there attempting a talk about databases? And that's a very good question. I totally agree with you. If you'd have told me a month ago that I'd be doing this, I actually wouldn't have believed you. So what changed? There were 2 reasons. One, this is my second bit of vulnerability. I'm very bad at giving interviews, like totally bad. I can never even motivate myself to read CVs. But I have come up with a technique to slightly mitigate that, which is to go into an interview and ask the candidate what they think they're most expert in. And then we start having a conversation about that, and then I get to judge how deep this guy really is into whatever that thing is, and you know whether our metrics of expertise line up or not. So I was actually recently doing this lazy interview technique with a guy on the phone, and in fact I think it was in person, and he told me that he was an expert in databases, right? And I'm thinking, shit, how am I going to blag this one? Well, anyway, so I thought, well, maybe actually this is kind of a learning opportunity. So I started asking him about indexes and how they work. And it became pretty clear that he didn't have a lot to teach me. But in the process of me trying to move the conversation on, I was making a whole bunch of like what seemed to me like fairly plausible explanations for what these mysterious things were. And anyway, roll forwards a little bit, the interview concluded, and I was just left with this feeling that perhaps it wasn't so mysterious after all, or that at least it was tractable, and that maybe I would be able to figure out if I actually put the effort in, which at the time I totally wasn't prepared to do. And then the other reason, this guy, Val, so it turned out recently that my employer and I parted company, and I engineered it in such a way that I had a lovely 3-month holiday, and towards the start of my lovely 3-month holiday, I decided to have lunch with Val, and he asked me if I had any ideas for a talk, and I'm like, shut you down, absolutely no fucking way. I've got 3 months paid holiday. No, I'm not going to do that. But unfortunately, he planted a seed in my mind, and I woke up the next day thinking, well, actually, maybe now is the time to grasp the nettle and to start demystifying this stuff. And one thing that I have learned over my career is that when you are trying to demystify black boxes, one of the most powerful techniques is to build your own box, because your own boxes are never black, right? So that's the first thing. And the second thing is commit to teaching people the thing about which you know nothing, because it's a really good fucking motivator. Yeah, I mean, I don't actually like being vulnerable, so fuck you, Brené Brown. But here we are. So this talk will be very roughly structured around that journey. So the talk is as much about my research as what I found, in a way, if that makes any sense. And I'll just be clear with you, like, if I was actually an educator, I wouldn't do the slides in this order. So no doubt those comp science students in the room, I need you to be patient with me, basically. So let's begin the story. So where do we start? Good question. Like, what actually is a database anyway? Yeah. So this is where I started. Yeah. As you can see, I'm an expert at using Google. And here are some of the things that my expert searching technique turned up. It's important to understand that there is no significant difference between a primary key, a unique constraint, and a unique index. To implement the concept of primary and unique key constraints, the database manager uses a combination of a unique index and the not null constraint. Okay. So this is saying that primary keys, unique constraints, those things are actually abstractions, and the abstractions are implemented in terms of indexes, and we can infer that indexes can either be unique or not unique, and we can also infer that they can be tolerant of null or not tolerant of null. Please take a note of the hyperbole fact checker at the bottom. I realised as I was preparing for this talk that I'd committed to hitting like 14 fucking facts and points, and I'm trying to keep myself honest. This is the first point at which something that I committed to explaining crops up. It doesn't actually make any more sense than it did before at this point, but this one actually comes up again. But yeah, so keep your eye open for those hyperbole fact checkers at the bottom. And I forgot to mention, this was my very first hit. And within that same hit, a bit further on, we get to this. Non-unique indexes are not used to enforce constraints on the tables which they're associated. Instead, non-unique indexes are used solely to improve query performance by maintaining a sorted order of the data values that are used frequently. So there's something else new here. Indexes can exist to improve query performance. We didn't note that before. And this is talking about non-unique indexes being used in this way, but obviously, again, we're back to inference. We can infer that a unique index can be used in the same way. And it's also mentioning ordering, which is going to be central to the story as well. So we actually learned quite a lot from that first technique. That first hit, so we should sum it up. So far we learned that indexes are used for identity via primary keys. They're used for constraints via the uniqueness characteristics of one type of index, and they're used for query performance. Is there anything else that they're used for? This is coming back to my theme that they're used for everything. They're the solution and the problem when it comes to databases. So let's continue. Clustered indexes sort and store the data rows in the table or view based on their key values. These are the columns included in the index definition. There can be only one clustered index per table because the data rows themselves can be stored in one order only. So here's another thing. Indexes are used to actually store the underlying data. And when they do so, they're known as clustered indexes. So what's an index when it isn't clustered? Non-clustered indexes have a structure separate from the data rows. A non-clustered index contains the non-clustered index key values, and each key value has an entry. Each key value entry has a pointer to the data row that contains the key value. So when it's not a clustered index, it's a non-clustered index. So coming back to what's an index for, we've learned the following. They are for table row storage, because each table has a clustered index, and that's where the actual data goes. Identity, the primary keys are actually that of the clustered index, and we learned that the primary or clustered index, I say indices by the way, it seems the rest of the world disagrees with me. Indices are now unique and do not tolerate null values, and this makes sense now. Retrieval, so an index we can also retrieve data based on a key. In the case of a clustered index, that's going to be the primary key, and for non-clustered it's going to be a secondary key, and then you've got constraints and performance again down at the bottom. In the interest of completeness, I should say that you can create a table without explicitly specifying a primary key column, and when you do so, what you end up with is something called a heap table. But guess what? Surprise, surprise! Behind a heap table is a fucking index, because indexes are the answer to everything, apparently. The difference there is that I guess you're all familiar with the auto-identity function. So when you create a heap table, it's a little bit like using auto-identity in the sense that a key will be assigned. It's just that that key is never raised up into like user space. You never get to see it. And the wizards tell you it's a fairly stupid way to create a table, and I'm with the wizards on this one. So anyway, this has all been very wordy so far. I'm not a particularly wordy guy, so let's visualize what we learned. So a table has a clustered index where the data rows live. We can access them via primary keys. It may have 0 or more non-clustered indices or indexes, depending on which side of the Atlantic you're from, and these can be either non-unique or unique. They can tolerate null or they can not tolerate null, and they themselves point to the data which is stored in the clustered index. This confluence of attributes here, unique and not null, is how we specify unique constraints. And finally, the non-clustered indices specify secondary keys in the sense that they're not primary keys. So nothing new there, just a visual summary. So what happens next? What data structure does SQL use for indices? Google. What data structure does SQL Server use for indexes? Fuck you, Google. Fuck you. You spelled colour wrong too. Oh, listen, he's actually listening. That's nice. Anyway, but really, what is an index? In SQL Server, everything is organised as B trees. So finally, we're actually getting somewhere, something concrete, something to Google further on. And up pops hyperbole fact checker again. Ever wondered exactly what an index is? Now we know it's a B tree, which is great, as long as we know what a B tree is, right? So let's Google that. In SQL Server, indexes are organised as B trees. Each page is an index in the B tree called an index node. The top node of the B tree is called the root. The bottom is known as the leaf, or the bottom nodes are known as leaves. Any index levels between the root and the leaves are known as intermediate levels. In a clustered index, the leaf nodes contain the data pages. We knew that. The root and the intermediate level nodes contain the index pages. Okay, that's kind of interesting. Each index row contains a key and a value and a pointer to either another intermediate level or in the B tree or the actual data row. And the pages of each level are linked with a doubly linked list. This is good stuff, densely packed information.
I have a question.
Go on.
Okay, by page, what do you mean by page?
That's a very good question, and there's a slide on that.
Okay.
If you can just hold on
I will
for
hold.
a couple more minutes. So I did a fair bit of research to find a really good quality visualization of that blah-de-blah that we just read. It seems like the internet is just full of very autistic people who are quite happy to read black and white diagrams, densely packed with nothing but numbers. What I quite liked about this is A, there's a bit of colour, and B, the index keys that they picked are characters, not numbers. And when we get into it, you'll see why it can be a bit confusing if we have these things called pages that we have to keep track of, but we're also trying to keep track of keys, and also column values tend to be numeric also. So I quite like this image for the reasons that I just explained. It's also nice that it actually shows a bit of row data. And yeah, it's simplified, and we'll talk a bit more about that later. But one thing that we can note straight away is that we can confirm that the data is indeed sorted. Top left is something that begins with A, and bottom right is something that begins with Z. Everything in the middle is where it should be. So yes.
So does this represent a tree? Like
yes.
The top level is the root and the leaves are the bottom?
That's exactly right. Sorry. That was the visual representation of this chunk of text here. So in those terms, the top was called the root, and these are pages. These are what that text was calling intermediate pages or index pages, and these are leaf pages or leaf, and they are data pages. This is where the actual data lives. So how would we use this data structure to actually find some data? Let's search for H, for example. How do we find H? Well, we have to start at the root. Well, conventionally we start at the root. We're looking for H. Is H bigger than A? Yes, it is. Is H bigger than O? No, it's not. Okay, so we have to follow the pointer from the A index, which takes us to page 60, which is another intermediate node or index node. Here we start at the top and we work our way down. Is H bigger than AI? Yes, it is. Is it bigger than CU? Yes, it is. Is it bigger than KR? No. So what do? We jump down to page 130, which is this page, and we do the same thing. Is H bigger than CU? Yes. Is H bigger than FE? Yes. Is H bigger than GA? Yes. Is H? Yes. Is H? Yes. Good. We're finished. Because this is clearly a unique index, the next thing is greater than H, and therefore not the thing that we're looking at. So that's how we use that data structure to find a particular key. And you'll note we did two kind of like jumps, two indirections to get there, and then a little bit of scanning at the same time. So how might we use that to do a slightly different type of search? Let's say we want to find everything that is greater than H. Well, we do a very similar thing to start with. I won't go through it again. We ended up at H, exactly the same as we did last time, but we now know that the thing that follows is indeed bigger than H, so we can yield that. And then we look for our next page pointer, which is taking us to page 140. We start at the top of that, and we don't even need to look anymore. Because it's sorted, we know that we can yield everything there, and we can keep going, jumping to the next page, yielding it all, and jumping again until we get to the end. And we know it's the end because the next page pointer is null. So we've made use of this doubly linked list that was referred to in the earlier documentation. And again, we made two of these indirections or jumps to get to the data that we wanted. But wait, what exactly is a page? Your question, and it's a well-timed one. So one thing that we've been taking for granted is that an index or a database is a durable data structure. And in computing, we've only really got one way of making things durable, and that's by using a disk. And in general, we think of disk access in terms of files, but it turns out that files aren't a particularly useful abstraction for databases. Although files are created, obviously, with SQL Server, most of what you consider to be the database is in the MDF file. But that thing is broken down into logical units, and those logical units are known as pages. Okay, so they're segments inside of a database file. And furthermore, those segments are read in batches, and the batch is known as an extent. So that's how I would describe it, but more formally, the Microsoft documentation describes it as follows. The page is the fundamental unit of data storage in SQL Server. An extent is a collection of 8 physically contiguous pages. Extents help efficiently manage pages. In SQL Server, the page size is 8 kilobytes, and rows cannot span pages. However, portions of the row may be moved off so that blah blah. Let's not bother with the rest. Yeah. So there's actually a great deal of information on this particular link. Out of all the slides, this was one of the most densely packed in, documents that I came across. It's kind of an interesting topic, really, because if you think about it, databases have to be necessarily self-describing, and they only have one unit of currency to be self-describing, and that's database pages. There's like a huge suite of types of data pages. Some pages are catalogs of other types of pages. It's really complicated, and it's really interesting, and it's way outside of the scope of what we're going to talk about. But if you feel like following it up, then take a look at that link. All we really care about today are data pages. This is the physical layout of a data page. It's really boring, so let's move on. Back to our example data. This wasn't immediately clear to me because I think I'm a little bit slow, but the sample data is in fact the periodic table, but it wasn't all of it. It's actually only partially filled, and I'm wondering now how we can insert data into this data structure, because we need to get the rest of our periodic table in there for it to be useful. And as we noted before, it's definitely alphabetically sorted. It starts at A and it ends in Z, so our insertion points aren't immediately clear to us. Let's just point out again that in our example we have 5 rows per data page. So to make it clear, I don't know what the resolution is like, but this says key, this says non-key columns. Like, this is indicating non-key values here. Like, it's probably a lot wider than 2 columns, and we can actually do the maths that proves that, because we know that a page is 8 kilobytes, and we've got 5 rows, so each row must be 1.2 kilobytes, and so far we've only got 3 columns, which can't account for 1.2 kilobytes, so clearly they've not displayed everything in this image, which I was raving about earlier, but we'll forgive them that. So how would we do something like insert GE? Does anyone know what GE is? Germanium, it's discovered in Geneva, apparently. So how would we insert GE? Because clearly it belongs somewhere in page 130, precisely here, after GA. So what should we do? Should we just chuck it in there and grow it? Well, we can't, because we're making the assumption that the columns are quite wide. There's no more room at the end. We can't do that. So what in fact do we do? Well, what's happened here, and it is quite hard for you guys to read, but we've grabbed another page. So we've gone to that catalogue of free pages that I referred to earlier, and we say, hey, give me a free data page, please. And one has come back, and it's page 300. And the next thing that we've done is we've gone back to page 130, and we've copied half of the contents out, or we tried to copy half, but it's an odd number, so we've only copied 2 rows. And we've removed those 2 rows from the original page. We've updated page 130's next page pointer to point to 300, and page 300's next page pointer points to 140. So we've inserted an extra node into, my diagram should have gone like that. So it's all appearing on one level. I did all of my diagrams on MS Paint, you can probably tell. It took me ages. Not this one. The Gandalf picture took me ages. We'll have to get back to that at the end. So this is known as a page split, and when SQL Server is doing that, the page utilization that it's looking for is between 50 and 100%. So when we created that new page, we put two rows in there. It was down at 40%, but the new row took it up to 60%. So now we have 2 rows at 60%. So we're fulfilling that criteria of page utilization, which SQL Server is keeping in mind, but you know what I mean. That's the target. There is actually a deliberate error here. Can anyone spot what it is? It's not deliberate or completely accidental, but there is an error here.
Inserted of G position.
Yes, thanks very much. So when I noticed that, I was a bit annoyed at myself, but then I realised something, which is that actually here, the way this space is used is a bit like a C program heap. Like you just start chucking data in from the top and it fills down. The things that are sorted are these things. That's my get out of jail card. It might be bullshit. I don't think it is bullshit. I think that's actually true. One more thing to say. I'm trying to keep this short because I know it's not the most interesting thing in the world, but there is another cheeky little optimization that SQL Server might make, and that's if it determines that you're trying to add keys in a sequence. If you're at 100% utilization, again, like in our example, like it was previously, sorry, then if we try to insert summarium, which is SM, we would get this situation. So it clearly immediately follows SE, but that's the condition that it's looking for. It's a heuristic to say, oh, this guy is inserting in order. If I just create a new page and put that one thing in, the likelihood is that he's going to do it again, and we're going to start filling this page. We get to do 5 inserts without any page splits. But if we were using the method that I talked about, we'd be doing more page splitting, and that's more disk I/O and more work for SQL Server. The wizards would not be as happy with us if we were to do that. So, so that's that. What I've described to you, this notion of page splitting is a form of tree balancing. The result of having a balanced tree is that all of your data nodes are the same distance from the root, and that means that your seek time, the number of what I was calling jumps before to get to your data, is consistent, because it would be super annoying to have a database where, you know, one time you issue a pretty straightforward query, it takes a certain amount of time, and the next time it's just like off the charts different. Consistency is king. We should move on. So there are a few problems that have crept in now. What happens if that guess about SM being added in order was wrong? That could be bad, right? And what happens if those guesses keep going wrong over time? We might have a whole bunch of bad guesses, like a guy having a bad day at the horses. What about rows being deleted? It's all starting to make my head hurt a little bit. Can't talk about it, I've got a splitting head. Okay, never mind. They won't all know. The result is fragmentation. Hyperbole fact checker. What is index fragmentation? This is index fragmentation, and it takes 2 forms. There's a form known as internal fragmentation, which is what I'm highlighting here. In fact, you can put a number on it. Internal fragmentation is an estimate of your page utilization, and yeah, you can put numbers on it. So here, this page is 40% utilized. This is 100. He's happy. This one is only 20. That's not great. This is 20. That's not great. 60. Yeah, it's all right. It's fine. It's within 50 and 100. 20 again. That's not great. And 100 there. So at this point, our internal fragmentation is about 50%. But bear in mind, we've only done a few operations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 operations to go from 100% down to 50. It's a bit of a tightrope. Why is that bad, incidentally? Well, just think about the number of indirections you have to start doing now. Like, the more pages you have, the sparser the data, the more following of the linked lists that you have to do, which is not ideal. The other thing is that between the database query engine and the disk, there's a cache, and it caches at page level. So if you start caching stuff that has one row in it, you've just blown 8K on one row, which we know is 1.2K. So your cache is going to shit really quickly. The other thing is that disks and disk managers, particularly physical disks, no one really uses that anymore, but even modern disks just way prefer sequential reads because they can prefetch, they can cache stuff. They don't necessarily write to the final storage layer. They also may write to an intermediate layer before it gets to the cold storage, as it were, because there are heuristics in disk managers also that make the estimation that you're most likely to read data that you've just written, blah, 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 right? So at many levels, this is a really shit thing to happen. The other type of fragmentation is external fragmentation, and that's referring to your physical layout becoming dissociated from your logical layout. So in this case, if we do our sweep through our doubly linked list, we jump from page 120 to 130 to 140, then we get all the way over to 833 to come back to 150 to go to 300 and back to 160. This is the same problem. This is going to give the disk controller a headache. So neither of those things are good. Some nitpicking. There's just one thing about what I've described so far in terms of B trees that is quite a big thing. They're not actually B trees. Once you start Googling B trees, as I did, you do come across some interesting things, such as they were invented by two guys working in Boeing. The B doesn't stand for binary, which is obvious when you think about it, because binary means two, and there were definitely more than 2 children per node. But they later came out and admitted that B didn't really mean anything at all. They just needed a name. So, yeah, I mean, that's the thing. That was the original B tree, and then sometime later there came some refinements to their original specification of a B tree. And the refinements were restricting data to only leaf nodes. We know that's what SQL Server is doing because the documentation told us. And to add the doubly linked list at each level, well, again, we've been told that that's what SQL Server is doing. So it appears that either the Microsoft documentation is wrong, or more generously, they were trying to simplify things for the sake of their audience. I think they may have forgotten exactly who they were dealing with in terms of their audience. So I think that we've probably got a pretty good understanding of B trees and B plus trees. Like, at least it's good enough for now. And we can come back to something that I passed over earlier. Non-clustered indices have a structure separate from the data rows. A non-clustered index contains the non-clustered index key and key values, and each key value entry has a pointer to the data row that contains the key value. So now we know more about the structures involved, we can visualize it properly now. You've got a clustered index there on the left and a non-clustered there on the right. The structure in terms of having a root node and intermediate nodes is exactly the same, and indeed even the non-clustered has leaf nodes. But the thing that is stored in the leaf node is a pointer which goes back to a data page which is owned by a clustered index. And we did say at the start that all tables have a clustered index, even heap tables have a clustered index. You just don't get to know about it. So back to the mission in hand, which, if you remember, was to build a database. I needed to find a library that could help me do so. Now I knew what I considered to be enough about B trees and B plus trees. I was raring to go. So this happened next. Like, I wasn't 100% clear on what I was looking for, but I was pretty sure that I didn't want some like shady, shonky one-man show GitHub implementation. I might put shady, shonky one-man show implementations on GitHub, but that doesn't mean that I want to use them, right? Because hell is other people's code. And clicking around the repos that I found, nothing there filled me with confidence. So I started to wonder if maybe that I was thinking about it wrong. Like, what I wanted to do was build the basics of the database and a querying system that used indices, but I didn't really care about durability at all. Doing durability properly is really hard. It's not something that you can do in a couple of evenings. There's so much there. Like, disk controllers, they lie to you. When you say, file save, your data isn't necessarily durable at that point. Like, there are so many layers between you that can lie to you. The operating system can lie to you. It can be doing write caching. The disk manager itself can be lying to you because it can do the same thing. There's caches all the way down. Has anyone heard of fsync? No, one, yeah. I mean, that kind of proves the point. Like, you have to go fairly esoteric to be sure that you're getting data onto the disk when everything between you and the disk says that it's written the data. It's quite hard. And I didn't want to get into that at all. And there's another factor, which is if you're trying to build a durable database and you use a durable data structure, you then have to go to the effort of making sure that you are consistent if you are in recovery mode. Like, otherwise, why would it be durable? And that's difficult, again, because now you need other parts of the database engine to make that happen. Like, traditionally, you have a component called a write-ahead log or transaction log or commit log. They're all the same thing. But you store some data off onto durable storage before you mess with any of these indices that we've been talking about. And it just seemed like a bunch more work, and I couldn't really follow. But while we're talking about it, I should mention that there is a class of solution to the problem that I'm talking about. The class of solution is known as a storage engine, and they do exist in library form. So, for example, if you wanted to Google it, Essent is the storage engine that used to power MS Exchange. I think they've moved off it now, but you can still grab Essent from Microsoft somewhere. RocksDB is another one, and there are a few more storage engines. But I didn't want to get involved in that. That was just like, that wasn't the purpose of the research. So what was it that I actually did want? I decided to go back to the source. What is so great about a B plus tree anyway? The mothership of knowledge, Wikipedia, came back with B plus trees are search trees optimized for being on disk. Okay, because I've just convinced myself that I actually don't give a shit about being on disk, so this is interesting. Unlike other self-balancing binary trees, the B tree is well suited for storage systems that read and write relatively large blocks of data such as disks. It's commonly used in databases and file systems. Yeah, we know that. That's how we got to this page. And talking of pages, this is confirming everything that I've been saying about pages and extents. Like, a B tree was actually specifically designed to be durable, and I've just spent 5 minutes convincing you that I didn't want that in my life. But what is interesting is this link to other self-balancing binary search trees. So what was on that list? A lot, happily. Although that was also a problem, because I didn't want to take the time to research all of them. That also didn't seem like a good use of my time. So I was actually quite lazy at this point, and I just used the most familiar. And I had at least heard of red black trees, and I was still trying to avoid the horror of other people's code. So I consulted my friend Google yet again, as follows. I don't know if you can read it. Red black tree, C# collection. And then the first hit is red black trees are important in practice. They're used as the basis for Java's implementation of the standard sorted set collection. There is no comparable collection in C#. Thanks very much. Brilliant. That's good news. Next hit, GitHub. Forget about it. Next hit is the same fucking thing. Forget about that. The next hit is a blog. So you know my policy on chunky code found on the internet. Forget about that. But wait. Is sorted dictionary a red black tree? I fucking hope so. That's certainly not shonky code. A glimmer of hope. Yay! It is! Great! We've got somewhere, finally. The guy, this is obviously a very old question. This guy's talking about Reflector. But it was promising, so I went straight to GitHub. And within a few clicks, I was looking at this. Can you see that? I'll read at least this for you. CoreFX source systems collection, source system collection is generic sorted set. And right at the top of the file, binary search tree is a red black tree if it satisfies the following conditions. And then it's listing out the conditions for what makes a tree a red black tree. And furthermore, they've even gone to the trouble of telling me which fucking algorithm book they've ripped it off of, which is nice. Incidentally, Robert Sedgwick, he's the one that people all over the internet reference in terms of these things. He's clearly the daddy when it comes to data structures. But one thing, oh yeah, I should say. So I grabbed the code immediately, because you can do that these days, and it's nice. Immediately started de-Microsofting it. It started at 2,000 lines. My version is 500, just saying. There's a lot of crap in this stuff. And there was one interesting thing to note along the way. And we haven't looked at any code yet, so let's look at some code. Now, it's going to be tricky, isn't it? Can we zoom this thing? Can I try? Tell me if it's pointless.
Can you switch maybe to IDE and zoom it in IDE?
I don't have it in the IDE. No, this is not in the IDE, trust me.
Okay, sorry. Then sorry.
But, oh no, it's not my PC. Sorry, it would have been easier if I was on my computer, but I'm not. So I'm going to go for it anyway. Look, so what it says at the top, public interface iSet, and it's got three methods. Add, remove, and find, all defined in terms of T. So that's your basic set interface, right? That's all you can do with the set. Well, you can enumerate a set too. Oh.
I'm trying to work with magnifier, but I'm not sure if it can work with other screens. Where's your presentation? Okay. Sorry for disturbance, but
That's right.
Did I just closed your presentation?
Maybe. How many good Chrome instances do you have? This one. So yeah, you did. It's right. Just, go to the history. Go to the history. The ellipsis on the end. That's not
it's not there. Sorry, I'll disconnect for a moment.
What slides? Like it should be in your history. Oh, that would be.
So this always happens when you want to help.
No more helping, please.
Okay, promise.
Can you make it bigger again? Oh no. Yeah. So as I was saying, so very simple set interface without removing find. The next thing is an implementation of that interface. The only reason it's there is for me to show you that it's constructed with an I comparer of T. Like that's really important, okay? So it's the set that's defined that makes use of an I comparer. This next thing here is called a key comparer, and it's an I comparer of a key value pair of T key and T value. You can give it a I comparer of T key, and then when it's asked to compare a key value pair, it defers down to the key attribute of each of those. Do you follow what I'm saying? So it's an I comparer of key value pair, but what it actually compares on is the key. And then what I've got here is what I've called simple dictionary, and that aggregates one of these simple sets. The simple dictionary gets a I comparer of the key. It creates one of these key comparers, and it passes that key comparer into the simple set. So now we've done all of that. This class aggregates a simple set of key value pair of T key and T value, and we can dig into that set using a key value pair, and only the key will be considered for equality. So when you get to implement the dictionary accessor, for any particular key, the first thing we do is we create a key value pair using the key that we were given, and then we can just put null, default, in that key value pair, because in actual fact, that isn't considered. It's not part of the equality check, only the key is. Then we dig into the set and we call find using this surrogate. And if we found it, then great. We'll return the thing that was actually in the set. The thing that was actually in the set doesn't have this trash null in it. It's actually got a real value on the value side of the key value pair. And you do a similar thing for setting. You instantiate a new key value pair. Well, it's not similar at all. You then check to see if you already had something at that key. If you did, you've got to remove it. And then you can put your new entry in. The reason being that sets, the idea of a set is exclusive membership. You don't have a set with a ton of things of the same value. It doesn't make any sense.
So what this does is basically a dictionary, right?
But yeah, I hadn't said it explicitly. I'm saying that you can create a dictionary out of a set with this trick.
Yeah. And why use a set and not a certain
because
dictionary? If there is one.
Because if you remember, we're trying to find a red-black tree, and red-black trees are implemented in terms of set, not dictionaries.
Yes.
But we are trying to build an index, and indexes are all about keys.
Yeah.
So we need to bridge the gap between set world and key access, or also known as dictionaries in .NET land, and which I actually think map is like a better name for. And in my code on GitHub, I actually called it a red black map because I think it's just slightly more intuitive. But yeah, that's why I made a point of explaining that. So back to red black trees. Actually, the source code said exactly the same thing. A tree can qualify as being a red black tree if it conforms to these rules. That's just really blah, and there are a number of very comprehensive explanations on the internet about how to build these things. Like, they're actually recipes. There isn't any craftsmanship left. There's no point in building one yourself. There's absolutely no point. You won't learn anything new. It's all been done before. There's no nuance. Like, even to the extent that every operation that you have to do to keep your tree balanced when you do an insert, every permutation of that is already documented. They're known as rotations, and there's a set of rotations depending on the color of the uncle of the thing you're inserting. Like, honestly, just don't even bother. It's not interesting at all. But one thing that is slightly interesting is that one of the attributes that makes a red-black tree appealing at all, in the face of all that competition, right? We saw a long list of binary search trees. You don't have to do many node movements when you're doing an insertion compared to most other implementations. Like the AVL tree is another very well-known one. You have to do quite a few node movements. It's really quite an unstable tree. And stability is a factor because, as I mentioned before, we want a constant insert speed and a constant remove speed. And although we won't go to it in detail, those speeds that I'm talking about are known as like that is the time complexity of an operation. There is a time complexity to an insert and a time complexity to a remove, and time complexities are described in terms of the big O notation, which everyone who did computer science will be super familiar with. The big O notation uses the little letter n to mean how many things in your collection you're dealing with, and these binary search trees hover around the O log n time complexity. But those claims don't make much sense if you have a really wide variance in your actual execution time. And what is nice about the red-black tree is that that is quite a small distribution because not many nodes move. So coming back to these complex rules about how they work, like we don't even care. And that's also not on the hot path of what we're trying to do here. We're trying to rebuild a database. Like, that's definitely getting into the weeds. We don't give a shit about that. So let's just worry about how we use them, because that we do need to know. Ideally, this example would have been in terms of the periodic table. I've mentioned a few times I'm super lazy. I couldn't be bothered to draw it up, so I grabbed an example off the internet, and we'll make do with that. So this is a well-formed red-black tree. As you can see, for each parent node, the left of the parent node is smaller than the parent node. The right of the parent node is greater than the parent node. Okay, so that's fairly consistent attributes, attributable binary search trees. And let's see how that is useful when we come to search for a value. So let's search for the value 7. Just like with the D trees, you always start at the root node. We have our search term, which is 7. 7 is 7 less than 12? Yes. Well, we should go left then because of what we just said. The left node is always less than the parent. Is 7 less than 5? No, it's not, so we should go right. Is 7 less than 10? Yes, it is. Bingo. We found 7. So that was great, but I'll just point something out at this stage because it becomes relevant in my next slide. There aren't any arrows on this diagram, so directionality isn't conveyed, but it is the parent nodes that have references to the child nodes, and there is no reference from the child node back up to the parent. and the references are in terms of like standard .NET object references. You could construct a tree where the children refer back up to their parent, but that's not what a red black tree is. And who here has kids? There's a good analogy to real life here. Parents tend to know where their children are. The kids don't give a shit where their parents are. The parents keep track of the kids, right? As the kids wander off. So when we move around the tree, it's up to us to keep track of where the parents are. And there's a data structure that we use to do that, and it's known as a stack. Does anyone want me to go into stacks, or are they all super familiar with stacks? Okay, so let's not even bother. The only thing I will say is that when you're using a stack, it's your choice. You can use a data structure, or you can use the stack. You can do it with recursion. In our example, we'll use a stack. So let's try searching for everything that is greater than 7. This is analogous to what we did in the periodic table when I asked to find everything that was greater than h. So the first thing we do is we drill down again, just like we did before, but this time I'm showing you the stack value. So the stack is this thing in the square brackets. Once we've got down to 5, we've got a reference to 12. Once we get down to 10, we've got a reference to 5. And likewise, when we're down to 7, we've got one for, what have I done here? Have I got that wrong? 10, sorry, never mind. So we are indeed keeping track of our parents, and we've just come across the object with our attentions. So what do we do next? We yield 7, and then we know of the properties that we know in a binary tree. We know that the parent is greater than the left-hand node, so we know we can do this. So we can pop and yield that thing too. And we know that the right-hand node value is greater than the parent, so that's also in scope for things that we're looking for. So we can travel down the right-hand node and yield that. And then we're kind of done with this part of the family tree. So we pop again, we end up back at 5, and we pop again and we're back at 12. And then we travel down the right-hand side, and we do a push again. So our stack is now, this one is wrong, I think that should be 15. And then we travel down the right hand node there, and we've incremented our stack on the way down. Not incremented it, we've added to it. And we can do the same thing. We start yielding and popping as we go until we get to the end. And then we'll see that what we've done is we've yielded 7, 10, 3, 11, 4, whatever you can read. We've yielded everything that was greater than 7, and we've done it in the right order, which is critical. Sorry? Did I forget 8? Oh, I did forget 8. I didn't even see 8, but yeah. Okay, noted. So the little set trick that I was talking about before, in practical terms it means that we are storing data at every node, unlike a B tree which stores data down at the leaf nodes. The little set trick lets us keep our data rows at the index key, if you know what I mean. Like that, it's the same thing. So here I've imagined that we have a order object which we're trying to index, and I'm using the order ID as the node key. So we're doing the converse of only storing data at the leaf nodes. We're storing our data at all the intermediate nodes. And this is in stark contrast to SQL Server, as we were repeatedly told, except, hyperbole fact checker, except in the case of something called a covered index. In the case of a covered index, SQL Server will store data at the intermediate nodes of a non-clustered index. And if you visualize what's going on there, it means that if you only have a small amount of data, you can create a non-clustered index where the index nodes hold that data itself. It means that that final bit of indirection back to the data pages of the clustered index, it doesn't have to happen. you can sort of cut it off at the source, as it were. Once you've done your traversal into the correct index node, you've actually got the value. So it's another place in which the documentation was lying to us. It's not the case that they only ever store data at the leaf node. Some final observations before we start coding. When a row is inserted or deleted from the table, which is actually the clustered index, we've got to update each index accordingly. That's pretty obvious. And when a row is updated, for each index we must check whether the value that was changed was part of the index key. Because if it was, then we need to rebucket that row. So let's take the order example again. If you had the orders like I showed you, with a primary key being the order ID, you may have a secondary index or non-clustered index which is indexing on the order quantity, something like that. If you change the order quantity on that order object, you've now got to move the item in the bucket on the non-clustered index. Did that make any sense? It will make more sense in the example. So let's move on. Time to look at some code. This is the code for managing the index, which is just, it's not super interesting, but it's worth showing you. Inside of Database Interactive, we have a type known as table. Oh, actually, how do we switch back now so I can, and that's all right, I'll just drag it up there.
Windows P and just duplicate it. Windows P, Windows P.
Okay, I'll do that. I'll get a neck ache. This code is going to look super messy because
Use a bit of wheel to increase the font.
I'm demoing. I'm showing you this on Val's laptop, not mine, and he has an old version of Rider. I'm using C#8, and his version of Rider doesn't understand any of the new language features of C#8. So, for example, this, like